Good day, guys, and welcome to our presentation. Today, we'll be conducting a comprehensive stability analysis using the Routh-Hurwitz Criterion. The Routh-Hurwitz Criterion is a method used to determine if a system is stable without having to solve for the actual use of the characteristic equation. In following this, you can easily detect any instabilities. In the next few minutes, we'll be taking you through the calculations and the final interpretation of our results. To begin with, we must first identify our characteristic equation, which is giving us s raised to the power 5 plus 6 raised to the power 4 plus 3 raised to the power 3 plus 2 raised to the power 2 plus s.
I'm going to cover the initialization phase of our analysis by initializing the array for our Routh-Hurwitz analysis. And we are going to use the coefficients of our fifth order system polynomial. So we start by using the s to the power 5 and s to the power 4. And so we are going to set this up, and for the row with s to the power 4, we are going to take the s to the power 5 itself, then to the third one 3, then to the fifth one, which is s, its coefficient, which is 1. That's why we have 1 3 1. And then for s exponent 4, we take its coefficient 6, we'll move to the next one 2, and then 1. So with this, we can continue to fill in the other values in our array, which is s3 all the way, s exponent 3 all the way to s exponent 0.
Now we move into the actual arithmetic phase for the s cubed row. We use a specific cross multiplication formula where the first element of the row directly above, which is 6, acts as our primary divisor. To find our first value, known as b1, we multiply 6 by 3, subtract the product of 1 times 2, and then divide that entire result by 6. For second value in this row, b2, we move to the next set of columns. We multiply 6 by 1, subtract 1 times 1, and divide by 6 again, which results in 0.83. Our third column for this row is recorded as 0 because there are no further coefficients in the original equation to pull from. This completed row now gives us the new pivots which we need to solve for the lower power of s.
Moving down to s squared row, we repeat our cross multiplicational process using the two rows that sit directly above it. Our new numerical pivot for this division is the value we just found, 2.67. To find the first element, c1, we multiply 2.67 times 2 minus the product of 6 times 0.83 all divided by 2.7 to get 0.135. For the second element in this row, we look at the last column where the value above it is 0. This simplifies the math significantly, allowing us to carry down the value 1.00 to fill the second spot. At this stage, our table is more than half finished, and we can start to see how the numbers in the first column are trending.
My name is Ebenezer Fusukwabi, and then I'm presenting on computing final row s to the power of 0. We finally reached the base of our array with the s to the power of 0 row. Even though this is the final row, performing the calculation is essential to complete the first column of our table. We multiply our previous pivot of negative 18.9 by 1, subtract the product of 0.135 and 0, then divide back by negative 18.95. As the identical term cancels out, we are left with a final value of exactly 1.00. This final step also provides a built-in safety check. The last element in the first column should always match the constant term from our original characteristic equation. Since our result of 1 matches the constant in our equation, we have mathematical confirmation that our work throughout the table is accurate, as shown in the table. Thank you.
On this slide, we can view the full route array in its entirely finished and polished state. When evaluating stability, engineers ignore the auxiliary columns and focus exclusively on the values populated in the first column. Reading down the column from the top to the bottom, our sequence of numbers is 1, 6, 2.67, 0.135, negative 18.95, and 1. The Routh-Hurwitz Criterion states that for a system to be considered stable, every single value in this column must have the same sign, that's typically all positive. We can clearly see that our sequence is interrupted by a negative value, which immediately tells us that the system's equilibrium is compromised. The table has done its job summarizing the numerical health of our fifth order system.
To conclude our presentation, we must interpret the data by counting the specific number of sign changes in that first column. Our value starts as positive, but we see our first sign change as we move from positive 0.135 down to negative 18.95. Almost immediately, we see a second sign change as we move with theorem. The total number of sign changes is exactly equal to the total number of roots that lie in the unstable right half of the S-plane. Since we observe two distinct sign changes, we know this system has two unstable roots, pulling it away from balance. Therefore, our final verdict is that the system described in example 5.6 is officially unstable. Thank you for following along with our analysis.